Hey everybody, welcome to another video discussing sequencing with signals in Max. So today we're going to talk about Euclidean patterns and the ways that the Euclidean algorithm can be used to produce rhythms in Max. And this is a pretty cool topic because of this paper by Godfrey Toussaint, who's now passed, but wrote this paper in 2005 in which he explains how the Euclidean algorithm, which comes from Euclid's Elements, allows us to generate very efficiently a large family of rhythms used in many types of music, particularly sub-Saharan African music, but also Indian music, Brazilian, many others. So, the finding here is basically that this kind of formal approach using mathematics to generate patterns has actually landed us with the result that people who are musicians find on their own, right? Of course, the people generating these rhythms, almost none of them were got there through the algorithm. They just got there through playing, through clapping, through banging on drums, whatever. But that structure that the Euclidean algorithm provides ends up sort of guiding the music. So we'll talk just briefly about what the algorithm does, how it has resulted in all these rhythms, and then we'll go ahead and implement it in Max. So most simply, what the algorithm does is computes the greatest common divisor of two given integers. And a result of that in a musical or sort of a rhythmic context is something like this. So we have two integers, the first indicating the number of steps. So in this case, that's 8 steps in a sequence or a pattern. And then 3 events within, or I think what he calls in the paper, onsets within within that sequence. So the two integers here are 8 and 3. And what the algorithm is responsible for doing is basically distributing the events evenly throughout the number of steps. So if you just give the algorithm the two numbers, it's going to make sure that as evenly as possible, given these sort of quantized steps, those events are spaced out evenly. And these are two examples here, which appear in Cuban music. So the first one on the left here is the tresillo, and then the one here on the right is the cinquillo. And you can see there's this syntax here, which he uses to describe the algorithms or the inputs to the algorithm. The first one being the number of events or onsets or triggers, whatever you want to call them, and then the second being the number of steps in the pattern. And if you go further down, there's a couple of sections, this one, and then another one down here where he actually just provides a list of rhythms and their Euclidean inputs. So, and there's some pretty wild ones. Like there's like a really long one down here. Yeah, this one. So this is pretty awesome, I think. You'll find as we start to work with this that the results that you get tend to be pretty musical, which is great. So cool. All right, so that's that. I'll leave the link to this down below. Let's go build that in Max. And today, the sounds I'm going to use are from Josh Spoon, who's a Cycling 74 person and also an Ableton Live certified trainer who has this package for Ableton Live of wavetable sounds that sound awesome. And I can't really do them as much justice as they deserve because I need pretty short, punchy envelopes here, which, this will do well, but I definitely recommend checking this out for like textural sort of pads and things like that. It's pretty massive sounding. So this is what we're working with today. And actually, I might just put a little low pass here. Cool. So link will be in the description for this as well. Sweet. So let's get into the patching. And first, what we might do is, before we start talking about implementing the algorithm, we'll just build the infrastructure a little bit to make us be able to make use of the algorithm. And these are things that if you have been watching this channel, you know about, but I find it's always nice to go through them, particularly because there's just many ways to do the same thing, which is pretty nice. So we're going to start with our combination of a transport and a phasor. And then we're going to pass that into a subdiv object. And we will use the probability feature of subdiv. So if I just set, to keep things simple to begin here, a basic subdivision of 16. Actually, let's do 8, just because it'll make my life a tad easier here. And then I pick an arbitrary pattern, which has 8 elements. I can use this prob feature that subdiv tilde has to actually just play back that pattern. So if I create a scope here, I'll start by I haven't sent it in yet, so we're just getting a ramp every 8 subdivisions of the main phasor here. But if I send this message, what it's technically doing actually is setting a probability for each of those 8 events. But because those values are 0 and 1, the probability is either 0 or 100%. And so this is a really easy way to just take a gate pattern like this and play it back. And then we can use a what tilde to turn those punctuated events. Actually, I've had issues with this in the past, and you've seen this video, or seen in other videos that I've done. So we'll do it this way. So we'll get an event when the ramp comes back down to 0. Cool. And we're going to keep things really simple this time from a sort of musical perspective, just to make it so the video is not too long. But we'll send, say, T60. So the value of 60. And actually, we'll do it like this. I60, so I can change it if I want to. But we're not really going to have any melody or anything. We're just going to keep things super simple. If we want to lower it a little bit, we can. 50. Cool. So now we're playing back that pattern. And that stuff is pretty much a rehash of stuff we've looked at in the past. However, now we get to do the fun part, which is actually work the algorithm into the mix here. So we know that there are 2 parameters that we care about. The first one is the number of steps in the pattern. And the second is the number of events. Okay. And there's actually a few ways to do this in Max. The easiest one is to do a thing where you basically say, first divide these 2 numbers by one another using floating point division. So if I have 3 events and 8, actually let me put something here. If I have 3 events and 8 steps, I get 2.6667. And then if I send into an Uzi the value 8, or the number, whatever the number of steps is, and then I divide each, and actually I need to, so when I pass the Uzi into 8, what I'm going to get is, with this argument 1, 0, which basically tells it when I've created the object, count just one bang starting from 0. But when I pass in an 8, it's going to override this first argument. So what I'm telling it to do is count to 7 starting from 0. And what I will then do is divide that number over our division between the steps and the events. And then what I want to do is take that as an integer and say, which basically is going to round it down to the integer. So this 2.6667 would become 2, and check to see, is it greater than the prior value? So what we're doing here is we have an Uzi, right? The Uzi is going to send out, and I'll print the result here. Let's do this. So we have 3, and then we have 8. And you can see here we get 0, 0.375, 0.75, etc. from this. We're going to then turn that into an integer. So the result that that's going to convert to will be like, I'll put a button here, this. And so then what we will say is, for each of these, for each number, is it greater than the prior number? And the way that we can do that is with this TII, where we first check to see if it's greater than the prior number, and then we put that number into the cold inlet here so that it is ready. It is there when the next number needs to be checked. And then we'll just group that. And this isn't exactly perfect, but let's just see what we get. We'll bang it when we're done. Let's see what happens. So we're close. So we're expecting to get for this 1, 0, 0, 1, 0, 0, 1, 0. But we got 0, 0, 0. So the reason is because the first one that comes through is 0. If we print that again. Oops. And we're asking, is it greater? Right? So what we could do is when we initialize this, we could send -1. And in fact, let's clean the whole thing up here. So now we're going to be checking to see, is 0 greater than -1, which it always will be. And we'll get the right thing. So now we get 1, 0, 0, 1, 0, 0, 1, 0. Great. Now, I want to be able to change this in the event that the events changes. Like if I change this value, nothing happens until I've actually sent a value from the steps. So I'm just going to do something to make that possible. So we can have here TVI. Bang here. And here. Great. So now anytime we change the steps, we'll get a new result. And I'll put that result in a message box here as well. So you could see 7 and 8. Great. Okay, get rid of this print. All right, now what if this value is 0? Okay, so if it's 0, we don't get the right result. If it's 0, we should just get all zeros. And the reason that's not correct is because we're always sending -1 here. So what we're going to want to do is store the number of trigs and say, if that is not equal to 0, then just check to see if it's equal to negative or equal to 0, and then multiply whatever that result is. So 0 if it's 0, 1 if it's not 0, by -1, and pass that in. And then here we will put a bang. So if I say 0, I get 0. If I say 1, 2, 3, great. So that's it. So if I do prepend prob, and I send it into my subdiv, and I run my transport, and I change. So we're getting and another thing that we need to do is make sure that the subdiv has the right number of events. So I'm going to say prepend div here, and I'm going to pass the steps number into the subdiv. So in this case, it's fine, but if we went to 9, subdiv would only be producing 8. Still, it would only be producing 8 subdivisions. So if I now change this to 9, this is the pattern we get. If we go 9, 9, let's check to see that it's working. We get no gaps. If I go 9, 8, then we should just see one gap somewhere. There it is. Cool. So that looks like it's working. Now, if you watch the polymeters versus polyrhythms video, which I'll put right up here, what we're doing here is actually the polyrhythm, which is the less usual thing, and might be what you want, but may also not be what you want. And the reason, what that basically means is, if we change the number of steps, then we're actually going to change the sort of granularity of our beat. So if I turn the sound back on, I'm actually just going to adjust this envelope a little bit. Cool. And I say make this 12. If I go say to 12, 12, that's what we get, right? If I say 9, 9, it's going slower. And that's because we're not changing the speed of this incoming phaser. All we're doing is taking a different number of divisions of a phaser of the same speed. So if we want it to be polymetric, then we can use a rate object to basically change the length of this incoming phaser, right? Because if we say, all right, I want a base subdivision of 16th notes. And that's actually, I think, the other video covers it a little bit, but a way that I like to think about the difference between polyrhythm and polymeter is the polymeter has a sort of static subdivision that is universal, whereas with the polyrhythms, that's not the case. So if we want polymeter, then we need a static subdivision. And what we're going to then tell the thing is, always have that be, say, 16th notes. And then it's just a question of whether we're counting out 9 of those or 12 of them or whatever, rather than actually, when we're changing this steps number, also changing subdivision. So what we can do here is just divide the steps number by the subdivision we want to use, and then pass that into the right inlet of the rate object. So you see if I hook up a scope here, right now it's exactly matching because the rate is 1. But if we say 16 and 9, now I get a shorter phaser, and you could see this is already sped up because now we're running at 16th notes rather than 9th notes or whatever. If I go to 12 here, we're getting a different pattern because we only have 9 events for 12 steps. So if I just go to 12, 12, you could see that the speed of the events, the density of the events is exactly the same, but now we actually have a different length phaser coming in. And we can hear the difference. 9, 9. It didn't change anything. So 9, 9, and 12, 12 are exactly the same thing as far as this thing is concerned, because it's just all. So we could actually have like a little toggle if we wanted to be able to switch back and forth between polyrhythmic and polymetric mode. And let me actually just quickly encapsulate this so that we're well organized. What we could do is have a toggle here and say that, you know, if it's the toggle is off, it will be polymetric the way it is. If it's on, then we will use polymeter. So what we'll do here is say cell 0, 1. Actually, maybe just cell 0. If it's 1, then we're going to send 1 here, because that means it's going to be, if it's 1, then we'll use polyrhythm, which means that we want the phaser that's coming out of the phaser object to be exactly the same as what, or we want the phaser that comes out of the rate object to be the same as what comes out of the phaser object. And we will take the inverse of this. So we'll turn 1s to 0s and 0s to 1s. And use that to gate the rate value coming from our little division of the subdivision in this step here. And in fact, that may be all we need. I guess the only other thing would be that we should probably bang the steps. So let's see if that worked. So if I say on, something's not working correctly, I should be getting 1. Maybe I need to turn that into a float. Let's try that. Oh no, that is working. But why did my pattern completely stop? Okay. So let's see. Oops. If I toggle this on, something's not working correctly. What is it? Oh, it's because I'm being lazy here about how I handle my ordering of events. So I have to go like this. Sloppy max patching. See, this is why being clean is important. Not all people think so, but I do, because of things like that. All right, so let's try that again. Great. So if we just stay with the simplest example, 11, 11, or even like 4, 4, just to really demonstrate, you could see now, because we're in polyrhythmic mode, the steps is changing the subdivision. If we stay in polyrhythm mode, it doesn't. Great. So let's encapsulate this whole thing. We'll call it poly mode. Great. Wonderful. And let's hear that result. So then, now we've got this thing built, and we can have our tresillo. Bum, bum, bum. Yeah, it's totally a Cuban rhythm. And then the cinquillo. Wonderful. So with these tools, hopefully you can go, read this paper, generate some ideas, and then just implement it here. What I want to talk about in the next video is, and I alluded to this in a prior one, the idea of using MC. Because if we use MC, we can have a sequence of objects that looks pretty much like what we have here on the left. But instead of just processing a single sequence, we could actually have many sequences. And I think that one of the exciting things that happens musically when using this approach is actually when you have multiple patterns that are running at the same time, either polymetrically or polyrhythmically, and you get really interesting intersections between the patterns. It's a really cool way to sequence percussion. It's also a really cool way to generate melodies in a bit of an unusual way, where you basically have multiple tracks of these Euclidean sequencers, each with different settings, and each of them plays a different pitch. And so then you can actually achieve melodies in kind of a with a different approach than what you would use if you just sat down at a keyboard or something. So with these building blocks, we can pretty easily make this Euclidean generator spit out 8 different or 6 or however many different patterns, and then have those all played back by a single chain of signal rate objects using MC. So that's what we'll talk about next time. And then I think probably I want to do a third video in this series where we just take that same MC device and implement the pattr system around it. So we haven't talked about pattr all that much in these videos. Pattr is really useful basically for keeping track of parameters. So in this particular case, we have, I suppose, kind of 5 of those. So our subdivision, our poly mode, our steps, our events, and our MIDI note value. And if we wanted to have, say, like a bunch of presets that allow us to create some configurations of this system that we like and then recall them, pattr is really useful for that. And when we're working with 8 of these sequencers and a lot of parameters, it can be pretty useful to be able to store those. So we'll talk about how to do that. As I wrapped up the video, I realized there's one small thing, which is cool, that I forgot and takes about 2 seconds to show. So I'm going to do it. Which is the ability to rotate the pattern. This isn't really part of the algorithm per se, but it's a really nice feature to have along with it. So I'm just going to show it. So if you watch what comes out here, and I have to send something through first. So we have this cinquillo pattern. If I put 1 here, I'm just going to shift this pattern to the right. So I'm just moving the digits rightward. So the pattern has the same density. We're just changing what it exactly is by shifting things back and forth. So that's another element of this this algorithm that is pretty awesome. And I'll actually, when I post the patch down below, I'll include this stuff in here. Yeah, so let me know if you have any questions down below, any comments. Again, the feedback has been really awesome. Check out Josh's synth, and I'll see you next time. Thanks. Bye.